All right, guys, it's the last class. I'm sure you're as excited as me. Um, what is there to say? I'll be in my office right after class. If people want to drop by with extra questions. Um, you're also welcome to sort of use this class as an office hours kind of thing where while we work on problems, I can just answer whatever else. The PSO will also be review problems kind of like this, so I encourage you to take advantage of this. And well, the videos are running late just because it's been sort of a busy week, so I'll probably get to it tomorrow or something. And that is it. Okay, so I'm ready to launch into the first problem. But any questions you want me to answer as a class? Of course, I can answer follow-ups in a moment. Okay, I thought this was a fun one. I'm not sure why I did that. Okay. All right. So again, all these problems are pulled from the Erickson book, which has lots of nice practice problems that I always recommend. There's several listed in the appendix. Okay. Okay. So let me read this out loud. Last thing I want to mention is that I've linked this PDF in the appendix as well. So if you wanted to load it up on your own screen or iPad, you can. Okay. Okay, so the famous puzzle maker, Canio the Dane, has invented a solitaire game played with 2 tokens on an n-by-n grid. So some of the squares are marked as obstacles and other grid squares are marked as targets. Or actually, one of them is marked as a target. And there's 2 tokens placed somewhere initially. And so each round, you get to take one of your tokens and sort of slide it as far as you can down or to the left, to the right, or up until it runs into a wall. I feel like I've played like Game Boy games like this. Like it's on ice or something. So until you hit the edge of the board, or you hit an obstacle square, or you hit the other token. So you can maybe try to cleverly bounce the tokens off of each other. The goal is to move either of the tokens onto the target square. Okay, so I guess in this example below, I mean the answer I guess is sketched on the right. Maybe that's no fun. But you have these 2 tokens, red and green, and you want to try to get one of them to land on blue. Okay, so if I was just to retrace the solution that's given on the right, you can move the I guess the red token here first, and then you can push the green token to the right, and that'll have it land here. Then you can move your red token to the left and run into that wall. I go like that. And you can keep kind of pushing it around the bottom. Like that. Push it to the right. Like that. And then lastly, you can push it all the way up. Like that. So each time we pushed a token, it went all the way until it ran into one of those black squares or another token or a wall. Okay, does the rules of the game roughly make sense? Okay, so so the problem is I give you one of these puzzles, which consists of an n-by-n board with some of the locations of the obstacles, as well as the target location and the initial locations of the tokens. And the goal is to try to figure out if you can solve this problem or not. Okay. So design an algorithm or show that this problem is hard to solve. That makes sense? I would say this is probably tougher than I would expect on the exam, but I thought it would be fun to do. Yeah, it doesn't have to be the minimum sequence of, yeah. I guess you're welcome to try.
I don't think I'm going to.
Okay. Maybe I'll take a quick poll just to make sure we're mostly on the same track. You have a choice between going for an algorithm or trying to show it's hard. So I thought I would ask which one you guys are leaning towards. Who is trying to maybe make an algorithm for this problem? Okay, just about everyone, and who is trying to show is hard. Okay, so okay, we got 1. Okay, good. 1 versus 100% minus 1. Okay. And then among those who are trying to make algorithms, if I told you most solutions fall into the camp of either trying to identify the right subproblem and use either divide and conquer or dynamic programming, some kind of induction stuff, or you're trying to change the input and reduce to maybe one of the more black boxes that we have. So I thought I would ask, who is trying to do something where you are trying to identify the right subproblem, some kind of one, okay? And then who was going for more of a change the input type of approach, some kind of reduction? Okay, so that's like... All right, so many people are trying to get algorithms that are something else. Okay, I will suggest, although this was a valiant vote, at least what I have in mind is trying to change the input to something we've done before. In fact, I don't know, you guys might be able to try to guess what's a reasonable algorithm or application to try to use. I'll let you guys work a little longer. Did you get it?
I don't think so. I have like process down, but
Pretty process.
thanks. I I don't know. I wouldn't be able to prove that if it's solvable, this will solve it, and I don't know how to prove. I don't know how to terminate it to like know that it's unsolvable if it is.
Are you taking? Is this within a change the input kind of?
I sort of. I didn't really find a black box. I just kind of made my own
Okay.
type thing. So basically, you create a graph, you map all the edges that it could go to, and then you just pick one. And so then you move it and you update the edges to then now what it could be, and then you just pick another one. But I don't know how.
Oh, sure. What is your graph? I mean, what are the vertices?
So all the cells are the vertices, and then I mark the target, the obstacles, and the tokens.
Okay.
And then you connect the edges between the tokens and like where they would stop.
Okay. And then I guess what's sort of tricky is you have two things moving around
Yeah.
on a graph. Right. Okay. So everything we're used to is only moving one thing, right?
Right.
Okay. I'll use that as.
So yeah, I don't think it would actually work, but it's just kind of what
Yeah.
I came up with.
But if it does work, that would be the hard way. There is a clean way.
Yeah.
So.
Okay.
Yeah. So you got to figure out, you know, the graph you drew is maybe the first one that or natural one that comes to mind. But at some level, as you maybe if you can make some kind of like enhanced or more meta kind of graph that can figure out how to you have a bigger, more complicated graph with a simpler problem on it.
Okay.
Right? That's often what's kind of going on is
Yeah.
how can I bake whatever big story is at play into a graph, maybe much more complicated than the graph initially presented to me,
Yeah.
but upon which the remaining task is more straightforward.
Right. Okay.
but position like the edges are for the red to move, and the green I just duplicate all the graph and make green faster. But I want to move like suppose the red is here, right? I can only move to this graph. I can only jump graph. So when I move the green, the red is here, right? So this edge connects the same cell together, and then but the green is moved. And then yeah, and I should leave it. Yeah, yeah. So it's like a complete.
So maybe as one last hint, I'll suggest I think we've had at least one PSO problem where we kind of moved two tokens at a time before. Oh, did I step on someone's?
I suggested it, but kind of.
Yeah, I don't know if the F bomb is necessary, but yeah.
This one. I look better. So there are n squared different GIs, n squared GIs, and then each of these can have so each GI can link to so okay so this can be moved in all n directions so can link to n from n other prefix. So that would be total of n square links. Then Q link, right? That's n square G and n square links. And each link can contain like n. No. Each link will have n square edges. Plus right? So how many total edges are there? So there are like n square. Okay, each one of one square can link to all of n other squares. So there are n cubed edges in one G. Right? So n cubed edges in one G. N cubed times n squared G and plus n5 edges for G total. Plus each this n squared link times n cubed edges link. That's n5 edges into G. So like n5 edges in G and 5 edges between G. It's still like 5 edges. And then this is one. Because the total nodes is n squared. N squared G times n squared. Yeah, that's less than this. So. But this one you can still use the same. That one you can use tree. Yeah, I don't know if it's I think it's really like your goal is better or better in other parts. I mean, it's not really seems to be. I don't know. And this is done. How is that we're supposed to see? It's even done.
Plot twist.
Okay. Uh, all right. Do people want to move on to the next problem? That's a big yes. Okay. Any luck, or maybe just brainstorming ideas that people tried, even if if it didn't quite get all the way there? Yeah.
Okay, so you need to construct a graph, basically, where there are n to the fourth vertices, essentially, but you're just using the cross product of all the potential like spaces on each graph. And that's how you're going to create this giant n to the fourth vertices graph. And you're only going to put an edge between two vertices if there's a valid move. So, like, for example, there's only a certain amount of spaces that the red token can slide to in a given state. And like, for example, in the starting base on the left, you only can go to 3 spaces with the red, which is the top left corner, the top right corner, and then if you go straight down. So you're basically just going to have this humongous graph of all these different states, and saying, like, if you can work from the source, which is where the red token starts, with the green token as kind of the helper, and you can work to the sink, which is the target, you just have to find a path in these different states where you can go from that source to that sink.
Okay. Yeah.
Programming this would be almost impossible, in my opinion. But I think theoretically it would make sense.
Okay. Yeah. Be bold. It's not impossible. But that's absolutely right. So just to help me out a little bit, when you make this graph, and we'll go into details in a moment, what algorithm would you submit it to? I know it's sort of implicit in your description.
We just said like DFS because you're just trying to find a path between the two.
Oh, perfect. Okay, so DFS is fine. I guess if you want the shortest sequence, you can try BFS. But so this is a can you get from one state to another state kind of problem, which is sort of like we did one of these last time, right? What did we do? What was the shortest path-ish problem we did last time? Okay, I don't remember. I'm blanking. Okay, but okay, so you're trying to the idea is that we can make a graph where each vertex corresponds to a configuration or a state of the game. Okay, so I saw many people doing something like this, and you know the game has rules, but from a particular state, there's actually a fairly limited number of other states you can go, which will actually make this graph sparse. Okay, so at a high level, what would be if the external information, like where the board is, I mean the size of the board and the obstacles and where the target is, if that's fixed, then what's the remaining information you need to know to understand where you are in the game? Racetrack was the other problem last time. Okay, so what information do you need to describe kind of one state? Yeah. Okay, so one state might look like maybe we write just a coordinate pair. Oh, I guess you need. Okay, so I might write like it might consist of like XR for the red's X coordinate, YR for red's Y coordinate, X green for the green's X coordinate, Y green for green's Y coordinate. Okay, so I guess this is where you're getting something like n to the fourth because that's how many combinations there are. Okay, and then maybe you'll make an extra source or supersync or something at the end, but that's most of it. And now at some level we'll add edges where you're allowed to go from one state to another state. Well, I guess I use primes to differentiate it. Okay, and you'll add an edge from here to here, you know, roughly whenever you can move a token and get from one place to another. So that means that probably only one of the two sets of the coordinates should change. Sorry, that Y should be an X. So only the reds will change or only the green ones will change, and it has to obey, oh, you ran into a wall or you bounced off a token or something. So you would, you know, write like 10 if statements here to sort out whether or not to put the edge there. Okay. It might be a little bit faster if you sort of start at the starting point, because the observation was given a particular starting point of tokens, there's really only like 4 moves you can do, so you only have to generate those 4 edges. So maybe you would instead write some local code to say, oh, I'll generate this is what it looks like if I went to the left, this is what it looks like if I went to the right, down and up kind of thing. So so we create this state space and we draw edges when you can go from one state to another, just based on the silly rules of whatever silly game we're analyzing in a particular moment. And then we run that's first search. If you want the minimum number of moves, you would run breadth first search. Okay, I guess the only other thing I should probably mention is that maybe you would make a super sync, because there's many possible ways to win the game. Any state with at least one token on the target square counts as winning. So I'll make an edge from all of those winning states to the super sync. Okay. So, but the main thing is you get some clever, cute story. And you know, can you go from state A to state B? You have to figure out how to encode the states and then how to describe the transitions between the states. Okay, and this is very much, for example, what people do in robotics and stuff like that when they're doing all sorts of planning problems where you have some limited number of motions and stuff like that. Okay, there's also NP hard variance, but that doesn't matter. Okay, all right, so that's a fun one. I get fun for me. Okay, all right, any questions? Oh, so this graph, if you did it fully, you should end up with like n to the 4 vertices and n to the 4 like edges. And so that would end up being your running time. I'll only note that if you wanted to look really, really carefully and get like a really faster running time, if you had a big grid, I guess, so to speak, and you sort of had like a bunch of empty rows in a row, you would never really be able to use any of those middle squares. So you can actually get rid of some rows and columns that are like very blank all around it. And then your size will roughly be proportional to the number of obstacles there are in the graph plus n. It doesn't matter too much. And the modeling is the most interesting thing for our discussion. Okay. All right. Here is Is that more fun than the next one? Yeah, okay, let's do this. Okay. All right, so this problem is about you and your nephew, apparently named Elmo. So you decide to play a simple card game, and the idea is that at the beginning you lay out a bunch of cards from left to right, and I guess they have point scores on them, like 10, or I guess king is worth 13 or something, and the rule is each turn I guess probably Elmo goes first because Elmo is younger, but Elmo chooses one of the outside cards. Okay, so maybe Elmo chooses 13 and removes that from the end, and then you get to choose one of the outside cards, and you get however many points as you take, and then Elmo takes an outside card, and then you get this, and then Elmo this. Okay, so you go back and forth, and the goal is to get as many points as possible. And we're going to look at two strategies. The first strategy we'll look at is when Elmo takes the greedy strategy, where Elmo's always taking the bigger card available to Elmo. But that's not necessarily the best strategy because it reveals other cards underneath and so on and so forth. And so your goal is to find a strategy that will beat Elmo whenever possible. Okay. Okay, so that's the high-level rule of the game. There's two problems associated with this, which I've erased by accident. One sec. Okay, so the input's going to be like the initial sequence of cards. Maybe it's like an array where A1 is one end of the array, and that's the first card, and AN will be the last one. So let's say there's n cards. Okay, and so the first one is to figure out the max number of points you can get against Elmo when Elmo's following the greedy strategy. And then a follow-up one that I just thought was interesting, it was also in the book, is if you have time or interested, suppose Elmo played an even sillier strategy where every time instead of taking the higher card, Elmo just took one of the two cards uniformly at random. Okay, and you promise that it's always random. And so maybe you can come up with a different sequence that maximizes the number of points in expectation, knowing that this is what Elmo will always do. But we'll probably focus mostly on the simple or the deterministic one, where Elmo's always trying to take the bigger card, and then you get to choose which outside card to take. Okay, does the Elmo's game make sense? Yeah.
Are the cards face up or face down?
The cards are face up. Yeah, you see all the cards, and yeah, you want to optimize this sequence.
No, 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 but if you take the highest, maybe this one is head. So you want him to, the better strategy is to take that low, then you take higher one, and then you take the even higher one. Next, yeah.
Oh, so for this turn, it's an action.
Yeah. Thanks. Like this. So I think he will choose to take or take left. So I try both. If I take left, and then so this is left at the bottom. Initial. So L1 goes first. So that's choosing right. One side. So I can either take left or take right. I just want to take out both. If I take left, then so if I have this right, I take left, and then next turn is downward right. So if this one is bigger, then my next turn will be like this. Otherwise take a right. If right is bigger, then my next turn will be like this. And right is smaller than left, the next turn I will have this. So then I just recursively call. So when I so the base case is if there's only one card, if there's only one card, there's no card. So right, J minus I is one, then I return as I. J is equal to I, then turn base 1 second. J is necessarily so basically is when I only have one card, then I will take that. Since every time you're running through this is your turn. And then if J is less than minus one. Yes. So each turn one even. Well, you don't know what you will get, so that's why you want to know. Because maybe there's a very big card like stout, and it's just one that two, three. And maybe you want to get all the small cards and then almost hit the big ones and then expose the larger ones. Maybe you want to lose a lot at first, but then you take the one that is the most. So you don't really know what's the best strategy. That's what I'm trying to do. Oh, no. So that's why we name people perfect. It's actually chess. So like, I have money left. Oh shit. And then we have to add stuff that you said the health statement is add. scroll the second screen. Yeah, the GS. I remember GS. Yeah, we do. And I'll just take that. And change less than means that I don't have any parts left. So I just put 0 means nothing. And then if there are some cards like either to the left or to the right, this is what I take the left, so I get the value at the left. And then I reverse two cases. So either the left, and then after I pick the left is bigger and the right is bigger. And then if the left is bigger, and then I'll take the second. Okay, so what is the so this is and then some problems and solve one time for some problems and then solve and then there is backwards speed, looking backwards. Does it matter? Oh my goodness. Yes, absolutely. But what we have I didn't understand behind the musician today. I have a question on the return. Similar. There's lectures is myself about the that's the only source. Still have to read. Why do I speak so? But I don't have time. I need to listen to the word what do you want to do? All Jeff. I don't know if you want to do it here. This is like this is a chance. On the test, you scroll back. All the Jeff is just good. Let's see all the Jeff problems. It's better than solved the problem. I didn't do that, but I saw that. So like I saw that problem. I didn't write it. I didn't write the solution, but I thought about the solution. So doing this, I know.
All right, I want to make sure we discuss the solution in time. So I'll get us started. Okay, so we'll start with that problem where Elmo is very greedy and always takes the bigger card. You had two choices. One was to argue that it's an algorithm. The other is to argue that the problem is hard. So for part A, did anyone try to get an algorithm? Okay, you and June. Okay. And then, so no one tried to show it's hard? Okay, we're all in agreement. And then, at a high level, between the two choices of trying to change the input or identify the right subproblem, did anyone try to change the input? We had half a vote for half a second. Everyone else tried to identify the subproblem in some sense? Okay. All right, so most are doing dynamic programming. I kind of knew this from walking around. Okay. All right, so who wants to, if we're doing dynamic programming, then who wants to maybe propose then a sentence to frame it? Yeah.
You have your algorithm that takes parameters I and j, which is going to be the max score we can get from cards within the indices I and j.
Okay, so I'll write MS for max score, and I'll define that as the max score possible with cards A, I through J. I saw many people had something like this when I walked around. Okay. As usual, sorry for the handwriting. Okay, so if we wanted to implement this, we can start with base cases or we can jump to the fun part. Let's do base cases first. What are some base cases for this sentence? Yeah.
If I is greater than or equal to j, return 0.
All right.
And also, if I is like the index right before j, just return the max card.
I is equal to j minus 1, return. Oh, so wait. In this game, who's going first? Elmo or who's going? Yeah.
We are.
Okay. And okay, so just keep it. And it's our turn. Is that fair? Okay, so if I is greater than or equal to j, return 0, and otherwise you'll take the better of the two. Okay. Everyone okay with that? I only notice one thing is just that if I is equal to j, does that describe there being one card left?
Sure. Yeah.
Okay, so
that far ahead.
All right, that's fine. So I think you mean 0 if I is bigger than j. That would be like 0 cards left. Probably just could have been built into a generic case, but I'll just bring it down. And if I is equal to j, then you should just take whatever is left. Or I guess you have to take whatever's left. Okay. All right, so those are 3 base cases then. All right, then what's the general case?
So you either take the right card or the left card.
Okay, so, yeah.
If you take the right card, card J, then you have to determine if Elmo's going to take card I or card J minus 1.
Okay, so we'll do AI plus, and I guess I'll do like if AI plus 1 is, I don't know what happens if there's a tie. Like, okay, let's say all the cards are,
different values.
they're all, okay, good. There's no ties. So if AI plus 1 is bigger than AJ, then you said Elmo will take the bigger one. So we would do, what would come here then?
I plus 2 comes
I plus 2 comma j. Otherwise, is less than aj, and you would instead write
I plus 1 and j minus 1.
I plus 1 and j minus 1. Okay, so that would model taking the left card. So you would take the left card. Otherwise, there would be something similar, I guess, for the right one. So I might just be lazy and pretend to write it. Okay, so or you can do something with the right, and depending on whether the remaining outside cards are bigger, figure out the appropriate subproblem to go into. So those are the two options. Now you have two options to choose, and you have to kind of decide one of them. So how would I sort of combine these two options, so to speak?
Return the maximum.
All right. We want the max score, so return the maximum of these two things. Okay. And then, of course, if you had instead solved the version where Elmo goes first, you would just kind of rearrange that logic a little bit. Hopefully, we can see how to do this. Did anyone try the randomized version? Yeah.
So I did it in where Elmo goes first.
Oh, you do where Elmo goes, yeah.
But so basically, instead of picking the max, you just pick one at random of Elmo's choices, and then like the rest of the algorithm stays the same. So then you make your maximal choice. Okay, so let me then recover everything. Let's start with the sentence for the sake of building habits on the last day of class. Okay, so I'll write max score R random, I guess. R for random. Yeah. This will be the max. Oh, maybe I should have wrote max expected score. Let's do the MES. Okay. The maximum expected score. Yes. Okay. Was AIJ cards remaining? Where Elmo is picking at random, so Elmo is 4 years old, I guess. Okay. All right. So, okay, and then and we go first in this version. Elmo goes first. Oh, sorry. Elmo goes first in this version. Okay. All right. So then if sorry, we're still catching up to your explanation. Okay. So I know this is boring, but what were some of the base cases? So first thing, you pick I or J for Elmo's choice at random. And then, so if Elmo picks I, then you increment I by 1. So then your remaining choices don't include that. So first, let me just say, okay, if I is greater than or equal to J, then Elmo will take the last card, so you get 0 points. In the general case, so you're just going to kind of simulate a random choice then. You're going to actually flip a coin. Yeah. And then based on that, then you go through your maximal normal thing. Then do math. Okay, so all right. So this is the idea then that's being suggested is if Elmo is going to be random, why don't I sort of bake in the randomness into my algorithm? Yeah. So then to get the expected value, just run it a certain number of times and average all of the maxes that you get. Okay, so if you simulate the experiment, will hopefully converge over time. Yeah, I got it. How would you even show that? Maybe I'll save that problem for my fall class. Okay, so but this is a natural idea that many people have suggested. Why don't we try to simulate it inside the dynamic program? It does get a little bit funky though, because at some level, well, let me suggest one thing. Well, I wrote this sentence, so maybe that's not fair, but we're not ever actually necessarily computing the maximum expected score. So if I were trying to argue that this simulated approach, so to speak, kind of works by induction or something, the first difficulty I have is that
I simulate and then I do some subproblems, and I don't even know if the subproblems are getting me the expected score, because those two are also kind of random and stuff. And then the only question, maybe over a long enough time horizon or something, right? But now, so it's getting complicated. So let me explain something. So what's kind of nice about expected value, so this is a little harder, but what's nice about expected value is it actually sort of takes the randomization out of the random experiment, so to speak, in the sense that you can have a big random experiment, right, and lots of chaos and stuff, but the average is just now a fixed fact, right? Like the average coin toss is 0.5, regardless of an actual coin toss out there. It's a kind of deterministic fact. So in the case of Elmo, and you can actually do this, and this you can actually justify and prove inductively. So you don't know what the outcome of Elmo's choice is going to be. It could be heads or tails, and we don't know because we haven't flipped the coin yet. But we do know that Elmo's going to flip a fair coin, and that fact is sort of like a deterministic fact. Okay? So what you can actually do is you can do, instead of sort of taking like, the max of this or max of that, you can do 0.5 of one outcome plus 0.5 of the other outcome. Okay, so again, this is maybe more for curiosity, but we could have done something like this, 0.5, and we will expand it in a moment, but sort of what happens if Elmo goes left, right? Because I know that Elmo will go left half the time. Okay, and then 0.5 of whatever I would do if Elmo goes right. Okay, so in other words, what we would do is, I would write something like, 0.5 of the time, 0.5 of the time Elmo would take the left card and go from I to I plus 1, and then we would choose the better of the two. So you would do 0.5 times the max of, like you guys just did, so Elmo already took I, so it'd be AI plus 1 plus I plus 2, J. Okay. Or you would consider taking the last one, which would be AJ plus, this also I would consider too hard for the exam, but I thought it was interesting. I plus 1, J minus 1. So in other words, you don't know the outcome of the coin toss, but you do know it's half probability. So I can sort of look through the experiment and just say, it's going to be 0.5 of that scenario where he takes the ith card, in which case I'll choose the better of I plus 1 or J. And it'll be 0.5 of Elmo takes the last card, and I'll take the best of I and J minus 1. And then you can do conditional expectation, actually show that works. Okay, but it's sort of just an interesting mix of dynamic programming and randomization. Okay, no sense. There was other fun problems listed below. They're posted online if you want extra practice. Otherwise, we're done, and I'll keep answering questions, and I'll be in my office after class. But not too late. I actually have a doctor's appointment around 3:45, so.